Electricity transmission is a foundational component of modern infrastructure, ensuring that power generated at distant plants reaches residential, commercial, and industrial consumers. Traditional transmission systems, which rely on copper or aluminum conductors, suffer from significant energy losses, especially over long distances. These losses, primarily in the form of heat, reduce the overall efficiency of power delivery. The use of superconducting materials in overhead power transmission offers a revolutionary solution. Superconductors are materials that, at sufficiently low temperatures, exhibit zero electrical resistance. As a result, superconducting transmission lines can carry much more electricity with minimal energy loss compared to conventional cables. This paper delves into the concept of overhead superconducting power transmission, its technological underpinnings, potential advantages, and challenges that need to be addressed for its widespread implementation. To address the challenges of increased electricity consumption, emissions targets, and aging infrastructure, the United States needs to substantially expand its transmission capacity. Research suggests that doubling or tripling global transmission capacity is crucial for meeting emissions targets. According to Princeton University, a 1% increase in the transmission installation rate above historical averages could reduce the U.S.'s 2030 emissions by nearly 20%. New solar and wind plants must be connected to electric vehicles and industrial facilities. Improved transmission infrastructure enhances reliability during normal operations and resilience during natural disasters, lowering system costs. Global electricity demand continues to grow by 1% to 2% annually, correlating with per capita GDP and living standards. Existing infrastructure also needs replacement. American Electric Power estimates that 30% of its transmission assets must be rebuilt in the next decade. However, building new transmission lines is challenging due to the difficulty in finding new corridors and the prevalence of NIMBYism. Environmental permitting and siting are significant barriers. Superconductors present a solution. They allow for the transmission of significantly more electricity than conventional conductors with zero electrical resistance. Though initially limited to projects requiring exceptional capacity density, superconductors will become more widespread as costs and perceived risks decrease. Their unique performance will drive innovation across power system infrastructure, enabling higher efficiency and lower losses in electricity transmission. Understanding superconductivity. The basics of superconductivity is a phenomenon where certain materials, when cooled below a critical temperature, lose all electrical resistance and allow electric current to flow without any loss of energy. This was first discovered by Heike Kamerlingh-Onnes in 1911 when he observed that the electrical resistance of mercury dropped to zero at very low temperatures. Superconductors exhibit several unique properties, including zero electrical resistance. Superconductors allow electricity to flow without any energy dissipation, making them ideal for high-efficiency power transmission. The Meissner effect. Superconductors expel magnetic fields when in the superconducting state, which is a key feature used in magnetic levitation technologies. Critical temperature. The temperature below which a material becomes superconducting. For traditional superconductors, this is often extremely low, e.g., below -150 degrees Celsius, though high-temperature superconductors HTS are capable of superconductivity at higher, more manageable temperatures. Types of superconducting materials. Low-temperature superconductors LTS. These materials, such as niobium titanium and niobium tin, require cooling to very low temperatures using liquid helium. High-temperature superconductors. These materials, such as yttrium barium copper oxide, have a higher critical temperature and can be cooled with liquid nitrogen, which is more cost-effective and practical for use in power transmission. Advantages of superconducting power transmission. Elimination of power losses. One of the most compelling advantages of superconducting power transmission is the near-total elimination of resistive losses. Traditional power lines, made of copper or aluminum, experience power losses as heat due to resistance. In contrast, superconducting cables carry electrical power without any energy dissipation, even over long distances. This translates to increased transmission efficiency. Superconducting power lines can deliver more electricity over longer distances without losing energy. Reduction in energy consumption. Reduced energy losses directly contribute to less energy consumption and lower environmental impact. Increased power transmission capacity. Superconducting cables can carry much higher current densities compared to conventional cables. As superconductors do not experience electrical resistance, they can handle significantly higher amounts of electrical power, making them suitable for applications in high demand areas and future urban grids. This means higher capacity lines. Superconducting cables allow for much higher power transmission capacity, reducing the need for extensive new transmission infrastructure. More efficient use of existing transmission corridors. Overhead superconducting transmission lines can carry more power through the same physical space, alleviating the strain on existing power grids. Reduced infrastructure footprint. The enhanced power carrying capacity of superconducting cables allows for the reduction in the size and number of transmission towers. This can lead to smaller and more compact transmission lines. Superconducting power transmission lines are more compact, requiring less space for installation and maintenance. Aesthetically pleasing solutions. In urban areas, the smaller footprint can help reduce the visual impact of transmission infrastructure, which is an important consideration in densely populated regions. Environmental benefits. Superconducting power transmission systems have a significant environmental advantage over conventional systems. Reduced greenhouse gas emissions. The elimination of resistive losses means less energy is needed to transport power, which can reduce the overall carbon footprint of power systems, especially when integrated with renewable energy sources. Integration with renewable energy. Superconducting systems are ideal for integrating clean energy sources, such as solar and wind, which are often located far from consumption centers. Their efficiency in long-distance transmission ensures that renewable energy can be effectively delivered to urban and industrial areas. Technology and implementation of overhead superconducting transmission. Cryogenic cooling systems. A major challenge in implementing superconducting power transmission is the need to maintain the cables at extremely low temperatures. Cooling systems are required to ensure that the superconducting materials remain below their critical temperature, and this can be achieved through liquid nitrogen cooling. For HTS materials, liquid nitrogen with a boiling point of -196 degrees Celsius is used as a cost-effective and accessible coolant. Liquid nitrogen-based systems are being developed to achieve a practical and scalable solution for large transmission lines. Cryocoolers are small, compact refrigeration units that can be used for maintaining low temperatures in localized sections of the transmission line, particularly in areas where liquid nitrogen transport is impractical. Superconducting cable design. Unit and overhead transmission are typically designed as composite cables, with a core made from superconducting material surrounded by insulation and a stabilizing layer. The design must address mechanical strength. Superconducting materials are brittle, and the cable must be reinforced to withstand environmental stresses and mechanical forces. Thermal insulation. To maintain the low temperatures required for superconductivity, cables must be well insulated to minimize heat ingress from the environment. Power conversion and protection systems. For integrating superconducting transmission lines with the broader grid, specialized power conversion and protection systems are required. These include inverters and rectifiers, devices that convert the AC power from the grid to DC power for superconducting transmission and vice versa. Fault detection and isolation. Superconducting transmission lines must have advanced fault detection mechanisms to ensure reliability and quick isolation of faults to prevent system-wide disruptions. Challenges in implementing overhead superconducting transmission. Despite the significant advantages, there are several challenges to the widespread adoption of superconducting power transmission. Cost considerations, high initial investment, the cost of superconducting cables, cryogenic systems, and supporting infrastructure remains high, making the initial investment a significant barrier. Operational costs. Maintaining the low temperature conditions in cryogenic systems adds to the operating costs, although this could decrease as technology improves. Scalability and integration. Infrastructure adaptation. Integrating superconducting transmission lines with existing power grids requires substantial modifications to grid infrastructure, particularly in areas that rely on traditional overhead power lines. Limited manufacturing capacity. The production of large-scale superconducting cables remains a challenge, with limited facilities capable of manufacturing the required lengths and specifications. Technological advancements. Improving materials. Research is ongoing into developing new, more cost-effective superconducting materials that can operate at even higher temperatures, reducing the need for expensive cryogenic cooling. Enhancing reliability. Superconducting materials are prone to failure if subjected to sudden thermal or electrical stress. Ensuring their reliability in long-term operation is a key area of focus. Future prospects. Overhead superconducting power transmission holds tremendous promise for the future of electricity delivery. With continued advancements in material science, cooling technologies, and power conversion systems, superconducting transmission lines could revolutionize the way electricity is transported, making long-distance transmission more efficient, environmentally friendly, and cost-effective. The integration of superconducting lines with renewable energy sources and the creation of high-capacity transmission networks will be key to addressing future energy demands and promoting sustainability. While challenges remain, the growing interest and investment in this technology signal a potential breakthrough that could transform the global energy landscape. Evaporated nitrogen must be replaced with additional liquid nitrogen, which is easily produced from air. 78% nitrogen and has a mature supply chain. Liquid nitrogen resupply plants can be spaced up to 100 kilometers apart, reducing footprint and cost compared to closed-loop superconducting systems. Despite these advantages, superconducting lines are initially more expensive due to added complications. However, they are competitive with conventional lines on a per MW/km basis and will likely be first used in high-capacity projects. As technical risks and costs decrease, superconducting lines will become more prevalent, driving innovation in power infrastructure and enhancing capacity and performance. The adoption of superconducting transmission lines will spur innovation in the power sector. These lines, with ampacities over 5 times that of conventional conductors, will require new high-ampacity substation equipment. Superconductors exhibit negligible resistance and can limit exposure to faults by returning to their resistive state under large currents. They also have no DC loss, except for the energy used by liquid nitrogen infrastructure. These properties will transform grid architecture. In summary, superconductors can help meet the growing need for transmission by efficiently transmitting more power in existing corridors. While more complex and initially costly, superconducting lines offer significant capacity advantages and will contribute to a more efficient, resilient, clean, and compact grid.